So welcome everyone to Geometry Week 3. So this week, we're going to be learning about circles. We've got angle properties of circles. So we've got these special rules that we can use to help us find stuff inside circles. We've got cyclic quadrilaterals, and we'll learn about what they are and some of their properties too. And then just some fun circle applications in the real world. Okay, so first off, we have this thing over here where base angles of an isosceles triangle are equal. Now this helps us with circles because we have this. So we have the radii, it's like radii of a circle, and they're all equal to each other, right? I'll just get a bit of color. There we go. So these two radii are equal to each other. So that means that this triangle that they make is isosceles, right? So that means that these two base angles right over here, they are equal. So if you have a triangle and it has one corner at the center of the circle and then the other two are like on the circumference, then that means that you've got an isosceles triangle. And yeah. All right, next we have the angle at the center is twice the angle at the circumference. Now there's quite a lot of rules today, so if you want to take notes or if you want to join me on the slide and follow along, that would be cool. All right, so for angles at the center, we've got I'll just change the color. Okay, so we've got this right over here, like that. So this angle here, we have, it's kind of like at the center, right? Like its corner, its vertex is at the center, and it touches the circumference at these 2 points, here and here. So if we have another angle and it also touches the circumference at these 2 points, but instead we join it to somewhere else on the circumference, so not joining it to the center, but somewhere else to the circumference, then we know that this angle right over here is double this angle. So this might be 2x, then this would be x in size. And for angle x, it doesn't matter where it touches the circumference. So it could be here or here, and all of these angles, they would be x. They would be half the one that's touching the center. Like that. All right, so this kind of leads us on to the next rule, which is that angles from the same arc are equal. So we have these two, and by on the same arc, it means kind of the arc that they're opening up to. So if we have this angle over here, and they've got this black squiggly line, that's the part of the circle, the arc that the angle opens up to. And this this angle is subtended on the same arc. So it's also opening to the same arc. So that means that angle A and angle B are equal. And from before, we know that C, it's on the same arc, but it's actually touching the center, so not somewhere else on the circumference. So angle C equals, I should get a bit of color. Okay, you can see it now. Equals 2A, and it's equal to 2B. That's double both of them because it's at the center rather than the circumference. And over here, we have more angles. So these are all on the same arc, they're all equal. These ones, yeah, I should stop outlining. It's getting a bit messy. But we have this angle right over here, and it's touching the circle at the same 2 points, right? But it's actually not the same as the other angles, and it's because it's opening up to a different arc. So these 3 angles, D, A, and B, they are all opening up to this arc right over here. However, angle Z, as you can see, is actually opening up on the other side, right? So it's like over here. So angle Z is not equal to the other 3. So just something to be a bit careful about. Alrighty. Just gonna, oops. Next slide. All right, here's another special property. So if we have a semicircle, and we can make a semicircle by drawing a diameter inside the circle, and then when we make an angle inside the semicircle, it's always going to be 90 degrees. So if it's like this, that's got 2 of these outer edges on the semicircle. I'll just draw in the semicircle. So this is the semicircle that we're looking at. So this angle right over here is 90 degrees. Now remember, we have a square to represent a right angle, 90 degrees. And this angle right over here. So all of them are 90 degrees. It doesn't matter where on the circumference they're touching. And same on this side. So we also have a semicircle on the right side. And then this one. Yeah, I think you get the point. Okay, so. Oops. Oh, there's a comic on the right side, if you want to read it. Okay, anyways, next slide. So we have the angle between a tangent and a radius. Now a tangent is a line that touches the circle at just 1 point. So for example, we have this one right here. So this tangent touches the circle at 1 point. So it's not going like this, right? Because that's like touching the circle at 2 points. And it's not like over here where it like completely misses the circle. So this one right here, we've got a tangent touching the circle at 1 point. And then we've got a radius. So the radius is like a line from the center of the circle to the circumference. And if it meets the tangent at the same spot on the circle circumference, then these 2 are going to make a right angle. Well, obviously, like if you have a radius like over here, then like it's going to meet the tangent like here or something, and that's not going to be a right angle. So they have to meet the circle circumference, both of them at the same point. All right, and this is always going to be 90 degrees. Oh yeah, and by the way, when you're writing your geometric reasons, you can shorten it to this part over here. So radius is perpendicular to the tangent. And I'm not sure if you've heard this word before, but perpendicular just means if 2 lines are perpendicular to each other, it means they're like cross each other like this, they meet at right angles. So like these 2 lines, perpendicular. All right. Next. Okay, now I've gone through quite a few rules, so we're just going to put it into practice now. We've got this one here where we need to find angles A and B. And whoops. Right, so we've got this 41 degrees here. And it's sitting on this arc. Right. So angle A is also sitting on this arc. So that means, and it's like going to the circumference. So that means that these two, they're both like angles on the same arc and they're both going to the circumference. So they must be equal. So A equals 41 degrees. And angle B. Now, you might be tempted to say that angle B is also 41 degrees. But remember that even though it's on the same arc, it's actually only going to the center. So it's only going over here. So we must use the other rule. So angles at the center are twice the angle at the circumference. So this is equal to double this one, double 41. So that's how we got 82, 2 times 41. Next slide. All right, so this one's a bit like more interesting. We've got some more things going on here. We've got angle in the middle, which is 96 degrees. Oopsies. And then we've got angle D. So we can just use the angles at a point add to 360 degrees to work out that angle D is 264 degrees. Now for angle C, we can notice that 96 degrees and angle C, they're both on this arc right over here. So that means that angle C is half of the angle at the center, because the angle at the center is double the angle at the circumference. So the angle at the circumference is half the angle at the center. So that means that C is 48. And remember, this only works if they're like on the same arc. Alrighty, and angle D, angle E is equal to this one. Now, this one's a bit more difficult to spot, but we've got angle D over here, and it's like a reflex angle. It's like opening up kind of backwards. So it's opening up to this whole chunk of the circle, this whole arc over here. And angle E is also opening up to the same arc. So that means that angle E and angle D, they're on the same arc, and angle E is at the circumference, whereas angle D is at the center. So the angle at the center is twice the angle at the circumference. So we've got 264 divided by 2 gets us 132, which is angle E. Alrighty. Now we're going to do some practice problems. So there we go. So feel free to annotate on here, or you can type your answers in the chat or unmute any way you wish. Now for some of these questions, you might need more than the circle property. So some of them might need like angles in a triangle. Others might need parallel line angle properties. So yep, good job, 107 degrees. Because we can see that angle C is on this arc right over here. And 214 degrees is also opening up to the same arc. 73. Yep, 73, perfect. Now, I don't know if you use the cyclic quadrilateral property, but we're going to learn that later on. But for now, we're just going to say that the way we can work this out is because we work out this angle first. So that would be 146 because the angle's at a point, add to 360. And then we halve that to get angle D because they're on the same part of the circle, the same arc. Yeah, good job. 98 is good. Right, for this question, you guys might need to find these two angles. So I'll give you a hint. So we've got this going on and we've got a tangent here and we've got a radius over here. Same with this side. Like that. 134 and 226. Yep, good job, Trinity. Alrighty, has anyone got any ideas for what this angle could be? So we've got a radius touching a tangent. So we've got a rule that says that the angle between the radius and tangent must be 90 degrees, right? So if I just mark that in here, like that. So now you've got this shape right over here. It's got 4 sides and you know 3 of its angles, 98, 90, and 90. So you could find this other angle right over here. So I've got a quadrilateral. And what do the angles in a quadrilateral add up to? Does anyone want to maybe type the answer in the chat or something? Yep, good job, 360. So we've got 360, whoops, what did I do? Okay. Yep, so 360. So this means that 98 plus 90 plus 90 plus y is equal to 360. So what would the remaining angle be? What would angle y be? You want to type the answer in the chat? All right, it's now 82. Oopsies. What have I? Okay. This one is 82. And, oh no, what did I do? Okay. Alrighty, and for the other few questions, these ones, I'll start you guys off. So for this question, we've got oops. Sorry, my laptop is just acting up a little. Oh, there we go. Okay, so we've got these two angles and they're angles on the same arc, right? Like that. And they're both going to the circumference. So that means that this one is also 21 degrees. Oh, good for Vina. Yeah. Alrighty. So just gonna clear that. Okay, so we have 21, 21, and right, what's angle A? Do you want to type your answer in the chat? Or maybe annotate. So I've got an angle at the center and an angle at the circumference, right? All right, so the answer is 42. And it's because the angle at the center is equal to twice the angle at the circumference, right? Okay, yeah, I think these questions are quite similar, so we might move on to the next slide. Oh wait, except for this one. So angle G is equal to, so I've got an isosceles triangle going on here, right? So does anyone know what angle G would be? Yeah, good job, 31. Alrighty, so G is 31. Nice. Right. Wow, good job, everyone. Yeah, it's 31 degrees. So now we know that this is 31. And then we have angle H over here. Okay, so now what have we got here? We've got a semicircle, right? And does anyone remember what the angles in a semicircle are equal to? Because if we can find this angle over here, then we'll know what H is, because we know that this part is 31, right? Yes, nice, 90 degrees. So angles in a semicircle are 90 degrees. So if this one's 31, then this one is, yes, nice, Trinity, 59. And Arangsa. Sorry, am I saying your name correctly? Arangsa. All right, and then we have this one. It's 59 as well, because we've got an isosceles. Alrighty. Clear the drawings. Okay. Next. All right, a couple more questions for you guys. Now we'll move through these a bit faster. So feel free to type your answers in the chat or annotate once again. By the way, everyone, for the questions that we don't get through in class, you're welcome to try them like after class sometime during the week, and you can like submit them to Google Classroom. After this lesson, I'll create an assignment kind of thing. It's by no means compulsory. It's just if you want to send any answers through to me, you're welcome to, and then I can give you some feedback. So like in the last slide, we kind of left a couple questions, so you could try some of those if you like. 33, good job. Yeah, so we have, no one should stop using purple. It's not very noticeable. Yeah, nice, because we have this over here, this neat radius to tangent. Yes, good job. So angle in a semicircle gives us 90 and 33 because angles in a triangle add up to 180. And just gonna zoom in here. Oh no, sorry guys, wrong slide. There we go. I think someone wrote 41 degrees for Q, and that was absolutely right. So good job. All right, for this question in the middle, it's quite an interesting question because we've got some symmetry going on. And I think Helena wrote that, 41. So we've got 41 like mirroring on both sides. So that was good spotting. Now we have, so for this one, you might want to annotate the diagram a bit more. Okay, so we have this angle right over here. So notice that this is a semicircle, right? So I've got angle in a semicircle is equal to 41 degrees. So we know that this angle here, we've got this triangle, right? So we know that this corner is 41, this is 90. So this angle must be, oh, actually, we don't even need to do that. No. So if you guys remember back to the exterior angle of a triangle, oh no, that's really bad drawing. So we've got 90, we've got 41, and we've got this exterior angle right over here. So the rule was that the exterior angle of a triangle equals sum of two opposite interior angles. Yeah, don't mind my handwriting. Sorry. Yes, nice. 22 degrees right here. Cool. So for these questions, for a lot of them, we're going to need more than one rule to help us figure things out. So we've got, this is also 22 degrees because we've got an isosceles triangle once again. So we've got 22 and 22. So the other angle in the triangle, right over here, this triangle. So we know that R must be equal to, should be 136. Yep, 136. And then we can use the angle at the center is twice the angle at circumference. So that's 68. And then for T, I think this was similar to another question. We had 90, 90, 136. So angles in a quadrilateral add to 360. So that gives us 44 degrees. And, oh yes, let's see. So for this question, 18 and 18 is absolutely correct. Good job. Because we've got alternate angles on parallel lines, right? And we've got like isosceles triangles. Alrighty, so we know that this one is 18 and this one is 18. So can someone tell me, so we know these two. So could someone tell me what this angle is? Angle M. So we've got angles in a triangle again, right? Perfect, 144. Nice job, Trinity. All right, I'll just speed through this one because we've got quite a bit more to go. Right, so we know that this is radius and tangent. They meet at 90 degrees. So we use angles in a triangle to figure out that this one is 67 degrees. Okay, and then angle U. So with angle U, it's a little bit more like complicated, I suppose. So we can use, so we know this is an isosceles triangle, right? And we have this exterior angle right over here. So we know that 67 is the sum of the two opposite angles. So angle U and this other angle that I've marked. And because this is isosceles, we can divide, we know that they're the same, these two angles. So we divide 67 by 2. So we get 33.5. And I have the answers down here. I'm just going to check that. Yeah, 33.5. All right. Next. Oops. All right. Got a few more problems over here. So this one needs maybe a bit of algebra for the bottom ones, especially for, whoops. Especially for this one, might need a bit of algebra. All right, while you guys think of some answers, I'll just start annotating the top diagram here. And then you can maybe work on some of the other questions on the board. I'll just start with this one. So we've got these two angles and they're on the same arc right over here. So that means that they're the same. So angle X is 32. And now we've got Y. We've got X is 32. We've got 113. So we can use angles in a triangle to figure out that Y is 35. Should be 35. Okay, so how about angle X, everyone? Notice that these two lines are parallel. So maybe type your answers in the chat. So what would angle X be if we've got these two angles inside parallel lines? Oh yeah, 63. Good job. And what type of angles are they? Maybe right beside your answer? Yeah, good job. Alternate angles. Okay, and by the logic of angles on the same arc, we know that Y, because X and Y are both on this arc, right? So what would Y be? They're both on the same arc. Yeah, 63. Nice job. All right, I might just do this question over here because it's a bit more algebra-y. For those of you that like algebra, here is your. So we need to be a little careful with this one because I think you have the right idea. So we have an angle at the center and an angle at the circumference, except it's actually the angle at the center is double the angle at the circumference. Yeah, it is a bit easy to get confused, but our rule is that we have this angle is double these angles and also like that one. So do you want to have another go at it? I think you had the right idea. You're really close. Yeah, good job. 8. Because we have 24 here. So we have 48 here. And then 6x is 48, so x is 8. All right, how about y? So we have two angles, they're on the same arc, and they're both on the circumference. So that means that they're both the same, right? Someone's chatted me. 6. Oh, so not quite 6. And the reason is because we have these two angles, 24 and 2y, they're actually the same because they're both touching the circumference. So if one of them was touching the center and another was touching the circumference, then the angle at the center would be double the angle at the circumference. But if they're both touching the circumference, then that means that they're the same. So 2y is 24. So y would be 12. All right. Might just move on to cyclic quadrilaterals now. Oh, forgot to clear the annotations. All right, here, and this is an interesting word, cyclic. Some people say you pronounce it as cyclic, and some people say cyclic. I'm fine with either, but I usually say cyclic. And cyclic just means that it's to do with a circle, and a cyclic quadrilateral is a quadrilateral. So a quadrilateral is a polygon with 4 sides, right? And so it's a shape with 4 sides that's inside a circle, and its 4 corners all have to be on the circumference of the circle. So they're all on the outside of the circle. And yeah, that's pretty much all there is to cyclic quadrilaterals. They have some interesting properties, as we'll see. So we have this cyclic, oh, whoops, sorry. So we have this cyclic quadrilateral here. We've got its 4 corners. And we go this shape right over here. So the two opposite angles, so that would be A and B, they're opposite each other. They always add up to 180 degrees. So if B is like, what does B look like? Maybe 40 degrees, then A must be 140, just as an example. And then same with these two, this one and this one. So this one might be like 100, and the other angle would be 80, like that. And from this, we can also derive another property. So because we know that A and B add to 180, we can have A, and we can write B as 180 minus A. Right, because if they add to 180, then this one is equal to 180 minus A. So we know that angles on a straight line, they add to 180, right? So angle C must actually be equal to A, because only if it's A, then you get 180 minus A plus A. So you get back to 180, right? So from here, we know that angle C is equal to angle A. And this is actually another special rule. This is the rule that the exterior angle of a cyclic quadrilateral, so remember exterior, this kind of angle that extends off the side of the quadrilateral. So this one is equal to the opposite interior angle. So it's equal to the angle that's opposite it on the inside of the quadrilateral. So these two. And when you're writing your geometric proofs, sorry, badly circled, but those would be your reasons, the short version. Oops. Oh no, my laptop is frozen. Sorry, guys. There we go. Okay. Here's an example. So we have a cyclic quadrilateral right over here. We've got these four corners. And what do we see here? We see that these two opposite corners, they add to 180, right? So we know that B must be 75. So 75 and 105 add to 180. And we have angle A over here. Now, angle A is next to this angle, which is opposite to this angle, right? So angle A must be equal to this opposite interior angle. This is 41. So A must also be 41. Oh, whoops. Sorry. I stopped sharing my screen by accident. I'll just share it again. Clicked on the wrong button. Alrighty. Can you guys see my screen again? Cool. All right. Just get back here. All right, we have a couple more practice questions. We'll just zoom through these because I've got some interesting applications, and then we have a Kahoot after this again. So, oops. So remember that opposite interior angles add to 180. So we have A and we have 81. So these ones are opposite, right? And we have the other rule, which is the exterior angle. Yeah, 62. It's equal to this opposite interior angle, right? Nice. Yeah, 107. Nice. And 73. Yeah, so we've got angles, opposite angles, exterior angle and the opposite interior angle are equal for the 107, and then angles on a line gives us U is 73. Yeah, 90 is good because we've got a radius and a tangent meeting. And down the bottom, 27, does it say? So that would be, I think it would be 22 because they add to 90 degrees. Nice. Oh, and some people are saying they can't see the Google slide. So, am I sharing? So is it that you guys can't see it in the classroom, or you can't see my screen right now? Oh, the screen. That's weird. Is anyone else unable to see my screen right now? Oh, I think most people can see it. So if you want to try like reloading your Zoom or something, that might help it. I'm not sure if it's like a Wi-Fi connection problem or something. Yeah, maybe try rejoining the Zoom. Thanks. Alrighty. We might just. Is there any interesting problem I want to show you guys from here? No, I think they're mostly more practice using the same properties. Yeah. Except for maybe I'll do this one with you guys. So we've got an isosceles triangle right over here. So we've got these two radii, they're equal to each other. Right, so we know that the base angles are equal. So if we have 46 degrees right over here, we know that the other two angles, they have to add up to 134, right? And so if they're the same, we can just halve 134. That gives us 67. So these two are 67. They're the same. To the top. Okay, 67. And for G, well, G is like, we need to use some other properties. So we have, oops. Sorry, just checking my answer right up here. So G, we have I think someone wrote an answer there, but do you want to rewrite it? I didn't catch it. Maybe it's like a flash or something. All right. So I've got 90 degrees, this corner. Actually, I might just clear everything. There we go. That's a bit clearer. So we've got this triangle here. We figured out that we have a right angle here because it's an angle in a semicircle. Earlier, we figured out that this was 67. Right, so we can use angles in a triangle to figure out that G is 23 because 67 plus 90 plus 23 is 180. All right, we have angle H. And notice here, we have a cyclic quadrilateral, right? So this is 67. So the opposite corner is 130. 114. Let me see. Yep, it is 114. Good job. And do you want to mark some of your other working? Maybe like you probably worked out J to get to 114. And maybe write in what J is equal to. So we have a cyclic quadrilateral. Yeah, 57. Because we have 123. We have 57. So they add up to 180, right? And then we know that this angle at the center must be twice the angle at the circumference. So we've got 57 times 2 is 114. And right here, we know that angle M must be, 21. Good job, Trinity. You're on fire today. All right, so 21, because we know that the radius, the tangent, must be at right angles, so 90. So yeah, that's 21. And oh yes, I will let Helena in again. Wait, I need to figure out how to do that. Oopsies. Okay, just gonna admit everyone. All right. So now sorry, just loading my laptop. All right, this is a bit of this slide has got a few challenging problems on here. So I'll leave it to you guys. If you want to do it as homework, you're very welcome to. I'll just I'll set up the assignment thing on the Google Classroom right after this class. And if you could submit your problems, sorry, not your problems, your solutions, then I will be able to give you feedback for these ones. We're just a bit short of time, so I won't do these right now. Yeah. Oh yeah, you might have noticed that I'm quite into puns. Don't know if you're quite as into them as me, but yeah. You know, just give you a little while to read it. And okay, so we now know that circles are actually not quite pointless, as the pun said. They're used in a lot of places in the real world, such as in architecture. So there's this thing called the Roman arch. Pretty sure you guys have seen this a lot, like they have like bricks and they build it up into these really pretty circular arches. So the reason that they do this is because circular arches are very strong. So it's kind of like if you and another person, you're like standing here and your arms are like pushing against each other, then you don't fall over, right? Because your weight and the other person's weight are like kind of balancing out. So you're like pretty stable. So the same thing happens in an arch. So we have the bricks or the ice in an igloo or something. So on both sides of the arch, they're like pushing against each other, both. So that means that they're very stable and they're like don't collapse very easily. Yeah, so that's the advantage of having circular things. And the same with domes. So the parts of the domes, they're all like pushing against each other and supporting each other in that way so that they don't tip over. The ancient Romans used it a lot, especially in their aqueducts, which they used to transport water across their cities. Because the aqueducts, they wanted them to be really strong, right? So they would use these circular ones. And yeah, here's some more lovely circles. Okay,